Hey, I'm Liam, and this is the 74LS181 ALU demonstration video. So in front of me is the demonstration circuit for this ALU, but before we go into that, I'm just going to talk a bit about what an ALU is. So the ALU is pretty much the number crunching part of a CPU, and it does the arithmetic and the logical operations, as the name suggests. So now that we know what ALUs do in general, let's talk a bit more about the pinout of this specific ALU before going into the example and demonstration circuit. So as I mentioned, this ALU is the 74LS181. In this ALU, there are two inputs, one input for an opcode and one output. Each of these listed inputs and outputs is 4 bits wide. In addition to these four main input outputs, there's also some supplementaries, like carry in, mode control, A equals B flag, and also carry out. Beginning with S0 to S3, or the select pins, these pins decide the operation that the ALU is performing in addition to the mode control and carry in. Mode control decides between arithmetic and logical operations, while carry in decides whether or not to add 1 to the result if it's an arithmetic operation. Next up is the A0 to A3 pins. These pins make up the 4-bit A input, and the same thing is true with the B0 to B3 pins. The output of the current operation is sent to the F0 to F3 pins. If needed, the carry pin will be set high, which is used for chaining ALUs together. Finally, the A equals B flag is a flag that will be used in chump for jumping. The A equals B pin is high when all F pins are high. So if we look at this demonstration circuit, what's going on right now is we have the operation not A. We can tell that because on this switch bank, which is the S inputs, we have all zeros. We can also see here that the mode pin is high. With the mode pin high and all S inputs being 0, then the logical operation is not A. We can see here that all the A's are 0 in the top nibble of this 8-bit switch bank, and therefore the output is all 1s and the A equals B pin is high. Now let's do another demonstration. Here, let's add A and B together. In this scenario, A is the top nibble of the switch bank and B is the bottom nibble. So firstly, because we want an arithmetic operation, we have to change the M input to 0. So you can see immediately that the output changes, and here, since all inputs are still low, we're actually just doing F equals A right now. And since A is still 0, then F equals 0. The select code for A plus B is high, low, low, high. So let's go ahead and set that. Let's go ahead and change A to be 8 by hitting its top bit, and then B will make 4 by sending the third bit high. You can see that the output of this is, as it should be, 12. The final thing that I wanted to discuss in this video is this custom ALU that I made in a program called Digital Logic Simulator. So this ALU is a very simple 4-bit ALU with inputs A here and input B here. So this is capable of adding, subtracting, bitwise ANDing, and bitwise ORing the two operands. By default, it's set to OR. You can see that we're currently ORing 1 and 4, which is 5, because these two bits are high and the rest are 0. However, you can see that if we switch up the opcode, which is these two bits here, we can change to subtraction. We can then subtract B from A, where we're now subtracting 4 from 1, and this gives us an output of -3. Note that these 4-bit numbers on A and B are using 2's complement, so the highest number possible is 7 and the lowest is -8. What this program shows is the inner workings of ALUs. While this may look pretty abstracted with an arithmetic unit and a logical unit, you can actually see that all these are designed from the ground. If I click on one and go to view, you can see that it's all made from smaller components, which I can continue to go into. Eventually, everything comes down to just AND gates and NOT gates. So essentially, this ALU is built completely from scratch using only AND and NOT gates. While it doesn't fully fit the description of this project, I learned a ton from making it, having to make all these special devices and components within this logic simulator. Let's take a final look at the logic unit, and you can see that it's also just made up of simple logic gates. Even the ORs are again made up of just and not. So with that, that's about it for this project. Thanks for watching.